get the basic idea, but eventually you get the details that you need for the implementation. So, pages for the kernel and for the user processes are both mapped in the same virtual address space. The virtual address space is actually divided. Okay, so virtual address space. Now, why do we need kernel pages? Don't forget that we actually have an OS here. Kernel that also needs to be executed. In fact, there's always something of the kernel executing. Otherwise, we're not even going to be able to get external interrupts or anything else, or let alone implement system calls. Okay? So the operating system itself is contending with this limited resource. Okay? That's why we have pages for the kernel. All right. This is 4 gigabytes. This is what Pintos uses as RAM. At least theoretically, it doesn't use the whole thing. But this is the virtual address space. It's not all mapped to physical address space, even though I have 16 gigabytes. Okay? We understand now that when I say a virtual address space that is 4 gigabytes, that is all possible demand, or that I can handle. Okay? So this is basically a virtual address space that I can divide into 4Ks and use for mapping. Okay? This is not how much RAM I have. This is not necessarily 4 gigabytes over 4K number of pages that I'm actually actively using. Maybe I'm using 5. That's it. It's still, this is Pintos' virtual address space. You'll see why this base here, which is about 3G, is called that. This is where a process can map its pages. This is where user process pages. This is where the kernel notice that these are non-overlapping. So one of our tests, in fact, the most prominent test for whether we are working with users' addresses and kernel addresses, with user processes being forbidden from accessing kernel addresses, virtual kernel addresses. This is one of our tests of whether we are, our memory accesses are valid. Okay, now the biggest difference here is that because the Intel architecture does not allow direct usage of physical addresses for examination of the physical memory, Pintus has mapped kernel pages one-to-one to physical pages. And that doesn't change. So while these are being swapped, depending on which process is running, so this could be 3 pages, then 4 pages, then 5 pages, then 1 page, then 0 pages, and 1 page, or so on and so forth, depending on whether we're running, currently running LSVEC or CP. Of course, we're not rewriting this memory. We're just changing this and doing the translation with different numbers, base registers and so on. Okay? The translation of the addresses. These are always the same. The mapping is always one-to-one to the physical pages. One-to-one to those. Okay? So that when you have the OS only have 4 pages because we only have physical pages, right? Okay. When I want to execute code that is here, the mapping is one-to-one to here. Okay. So the virtual address is actually equal to the physical address. That's why this is called physical base. Okay? Very important. Because you're going to see when when you start reading about the system calls, that the mapping of these pages is going to be to kernel pages. Because they're equivalent to the physical pages. With the mapping, that doesn't mean that they have the same addresses. Okay? Those are different pages. One is here. New page. But it corresponds to exactly one K page. Okay. So yeah, this is a nasty trick, right? After you learn about the equivalence of all these programs here in the way they compete for mapping here, Pintus actually maps one-to-one so that we can debug the real memory. So for kernel development, this is necessary. And this is Pintus's way of doing it. Okay. Now, you have to very faithfully do your reading and do your thinking so that we can get as soon as possible to where you know what questions to ask. Because right now you're not there, you're not even close. I'm only scratching the surface. but with enough application, you'll get there. Now, remember why I need you to read beforehand, so that you basically have a context in which to put my answers and my teaching. Okay? Right now you don't. Only half of you have sort of read it. Okay. It's about 8 or 10 hours of reading and thinking and drawing and going back and forth to actually get the picture. If I start telling you how to implement argument passing, I don't even have a context where to start. Okay? So I need you to do that. And we can't wait until next Monday. We need to work on Slack, get there, do the reading, ask me questions. Is this way or is this that way? I don't understand the manual here. The book says this, but the manual doesn't exactly use the same language, so what is it here? Or is it a design decision or something like that? And don't forget, read the source code. It's very well documented. A lot of the details are there. The comments of the source code, and then the source code itself. Okay. Now, what source code should you read? You know that each of the assignments starts with a section on files. Source files. So you should definitely read those. If you've already gotten the fact that in the frequently asked questions, the first one is how much code should I write, it actually shows you which files of the base system you should modify. Now let's start practically here. How many of you know how to execute the tests for P2? Okay, so at least one in each team. Okay, that's good. So the instructions that I posted in announcement should work. You've tried that? Yeah. Okay. There was a mistake there, and I had to correct it. I think it's fine. Okay. So read the files. I think this is chapter 3. All of chapter 3, and definitely the part of the reference guide that starts on page 72 with section A42. All the way, but not including section A8. Okay. Let's take a break for 5 minutes. And let's start the workshop.